Here's an example of using integrals to compute work, the amount of energy required to perform a task. We'll start with a preliminary example that doesn't require integrals, just to make sure that we're clear on all the formulas that we need. For our preliminary problem, let's find the weight of a 0.3 meter by 0.5 meter by 1.2 meter tank of water. So since we have the 3 dimensions of this rectangular box-shaped tank of water, we can easily find the volume. Volume is just length times width times height, so it's going to be 0.3 meter times 0.5 meter times 1.2 meters. And of course, when we get 0.18 cubic meters, pay attention to the units here. We multiplied meters by meters by meters, and we got meters cubed. That's the volume, but how do we find the weight? Well, first we need to find the mass. So in general, mass can be computed by taking the volume times the density. As long as we know the density of water, we're all set. The density of water in metric, I'll write down here in the lower left, the density of water is 1,000 kilograms per cubic meter. Now that's true when water is at its most dense, which is at about 4 degrees Celsius, and if it's pure water. If there's anything else dissolved in that water, or if the water is at a different temperature, the density may be different. But we'll just take this assumption for now. So our mass is going to be 0.18 cubic meters times 1,000 kilograms per cubic meter, and that gives us 180 kilograms. Now, how do we find the weight? Well, we can compute the weight by taking the mass times the acceleration due to gravity. That's g. G, I'll put over here on the left, is acceleration due to gravity. And on planet Earth, the Earth's surface, in metric, that is going to be 9.81 meters per second squared, approximately. So the weight of our tank of water is 180 kilograms times 9.81 meters per second squared. That will give us 1,765.8 kilograms meters per second squared. The units, but we call that a Newton. Newton is a measure of force, in this case weight. So that is the weight of our tank of water. Using that information, how much work will it take to lift the whole tank 1.5 meters? Well, we're going to now raise the whole tank 1.5 meters. That means that this distance from the bottom of the tank originally to the bottom of the tank in the end is 1.5 meters. That is our distance that we're moving our tank. And the weight of our tank, we determined, is 1,765.8 newtons. How much work does it take? Well, work can be determined by taking the force times the distance. This is force, which is the weight in this case, and d is the distance traveled, or the distance along which that force is applied. Okay, so our work is force times distance. That is 1,765.8 newtons times the distance of 1.5 meters. That gives us 2,648.7 Newton meters, except instead of Newton meters, we'll call these joules. 1 Newton meter is 1 joule, and that's the measure of energy or work we'll use. So the main takeaways from this example are two things. One, to find weight, most of the time you'll be able to work out the volume of whatever object you're interested in using formulas from geometry or maybe from calculus. But you'll take volume, you can multiply this by density to get mass, and multiply that by g, the acceleration due to gravity, to get weight. Okay, and recall that the density of water is 1,000 kilograms per cubic meter. If you're working with a different substance, the density might be different, but you can look up the density or find out what the density is. And g, the acceleration due to gravity, is 9.81 meters per second squared. Also note that if you're working in imperial units, such as feet and pounds, then you'll probably go straight from volume to weight because the density will be given in pounds per cubic foot or something like that. So you won't need to multiply by g because you'll already know what the weight is as soon as you use the density. The other takeaway, work equals force times the distance over which that force is applied. Force is usually weight for the problems that we'll do, and the distance that that force is applied you'll have. Now let's look at the main problem we want to solve. Suppose a spherical tank with a radius of 1.5 meters is half full of water. How much work will it take to pump all the water up to a height of 3.5 meters above the top of the tank? Now we can't just compute the weight of this water and multiply it by 3.5 meters this time, because the water is not moving 3.5 meters. In fact, the water at this level is moving a total of 3.5 plus 1.5 meters, that's 5 meters. The water at the very bottom of the tank is moving a bit farther than that, that's going to move 6.5 meters. In fact, every level of water that we look at is going to be moved a different height. So computing the work for this is not going to be as simple as just finding out the weight of all the water and multiplying it by the distance moved, because every portion of water you look at will be moving a different height, a different distance. So let's try and break this down. I'm going to redraw our diagram. Here's our spherical tank. There's a pump that probably goes to the bottom, but I won't draw that part. I'll just draw this part up here. This distance here is 3.5 meters. The radius of the tank is 1.5 meters. And as we've done in some previous examples in class, what we'd like to do here is create a coordinate axis that's convenient to us. That axis is going to go from here down to the bottom of the tank. There's some important points right here and right here. And we should decide what variable do we want to use for this axis, and where do we want to place the 0 on this axis. I would suggest we put the 0 right here at the center of that tank for reasons that will become clear in a moment. Now we can decide whether to make the positive direction up or down. I think I'll make it up. That means that this point here is 1.5, and down here we have negative 1.5 because the radius of that sphere is 1.5. Now, 3.5 units above the top of the tank is where the water is being pumped up to. That is 1.5 plus 3.5, that's going to be 5 meters right up here at the top. 5 meters above the center of the tank. Now, as always, if we're going to set up an integral to solve our problem, we'll need to decide how to break up our problem into small pieces. The logical thing to do here is to look at the water at any given level or depth. The water at some particular depth down here, all of the water that's at this depth is going to be moved up the same height, the same distance. So if we can find the weight of the water that's at a particular depth, we'll know how far it's going to be moved and how much work it takes to pump that particular section of the water. So we're essentially going to slice up our solid tank of water into slabs that are horizontal, that have some cross-section. In fact, all of these slabs will have a circular cross-section, but they will all have different radii depending on where you are. The slabs of water down at the bottom will have a radius close to 0. The slabs of water near the top of the water will have a radius close to 1.5 because that is the radius of the sphere as a whole. I'm going to decide to use the variable y for my axis here. So I'm going to talk about the yth slab of water. The slab of water at position y. What it really looks like is basically a disk, kind of like the disk we would use to find volume back in section 6.2. We need to know what the radius of that disk is. Now, I don't want to use the letter r for this radius because I'm already using the letter r. I'll pick a different variable. Maybe I'll call that x. How can we figure out the relationship between x and y? Y is the position of that slab, and x is the radius of that. Well, I'm going to move my coordinate axis a bit. If I place my coordinate axis so that the origin is at the center of my sphere, then we can call this the x-axis and this the y-axis. And guess what? We know how to find an equation that relates the x and y to create a circle in the xy plane, a circle with radius 1.5. That equation is x squared plus y squared equals the radius squared, which is 1.5 squared. Now be careful. 1.5 is the radius of the entire sphere as a whole. X is the radius of the one particular circular slab of water that I'm talking about. Now we just need to write x in terms of y, because y is our variable here. So let's just solve for x. X equals 1.5 squared minus y squared, square root of that whole thing. Okay, and how do we find the volume of this particular slab of water? Well, we know the radius of it, and we also know that its thickness is dy, because it's that very, very tiny change in y. So the volume of that little slab of water is going to be pi times the radius squared times the thickness, which is dy. I'll just fill in the value of the x here. This is going to be pi times the square root of 1.5 squared minus y squared squared. That's just 1.5 squared minus y squared times dy. That's the volume of that slab of water. Notice that our x had a square root in it, but because we're squaring the x, the square root has gone away. Now, how do we find the weight of that slab of water? Well, we already discussed this. We know that to find the weight of something, knowing the volume, we just need to multiply the volume times the density to get mass, and then multiply that by g, the acceleration due to gravity, to get the weight. This is going to be pi times 1.5 squared minus y squared dy times the density, which is still 1,000 kilograms per cubic meter, times g, which is 9.81 meters per second squared. I'm not going to write the units this time. This is not a terribly complicated formula. It's a function with a bunch of coefficients, but we don't need to worry too much about those. Now that we've found the weight of the Wythe slab of water, the question is, how far do we need to move that particular slab of water? Well, our slab of water is at position Y, right here, and it needs to go all the way up to position 5 meters, right here at the top. How do we always figure out the distance between one y coordinate and another y coordinate? We subtract them. So our distance that that particular slab is going to move is 5 minus y. Notice, by the way, that all of the water is 5 meters or more below the place where it's being moved. That's because the tank is half full and the middle of the tank is 5 meters below where we're going. But our y values are ranging between negative 1.5 and 0. So our y will always be a negative number, which means the distance will always be more than 5. But what distance it is will depend on exactly which y we're talking about at any one moment. At last, we're ready to put together our integral to find the total amount of work needed to pump all of the water from the tank to a point 3.5 meters above the top of the tank. Our work is going to be force times distance, but we have to add up the work that it takes to move each individual slab of water. That's going to be an integral. And it's the integral of pi times 1.5 squared minus y squared dy times 1,000 times 9.81. That's the weight of that slab of water, times 5 minus y, the distance that that slab of water gets moved. And the integral goes from negative 1.5 to 0, because that's the range of y values that cover all of the water that's in the tank. If the tank were full, the integral would go from negative 1.5 to positive 1.5. But because the tank is only half full, the top of the water is at position 0. And we'll just clean this up a little bit, pull our coefficients out in front. 1,000 times 9.81 is 981 times pi. And we have the integral from negative 1.5 to 0 of 1.5 squared minus y squared times 5 minus y times dy. Now again, this is just the integral of a polynomial. You know how to do this. It'll just take a little bit of care to make sure that you do all the steps properly and get your negative signs right and everything like that. So do this integral slowly and carefully so you don't make mistakes. But in the end, you should get 30,770.9 approximately joules is the amount of work that it takes to pump all that water out of the tank to the point above the top of the tank.